Okay. So James Webb, and these slides, many of them I stole from Jason. He knows about it. I stole it from them. So Webb is the mission lead. It's a joint NASA, ESA, Canadian Space Agency project. Strong participation from Europe. Being built largely by Northrop Grumman. Where Space Telescope is going to be the Science Operations Center, which means that we'll do the scheduling and so on, and the instrument support in the same way as for Hubble. It's a deployable infrared telescope, 6.5 meter, segmented, cryogenic temperature control. This structure here is the sunshade that always has to be between Webb and the sun in order to keep everything cool. It'll launch on an ESA Ariane rocket in 2018, October 2018. August 2018, I think it is. A 5-year mission requirement and a 10-year science mission goal. It's named after James Webb, the second NASA administrator, who was basically oversaw the bulk of the manned spaceflight program there. Hubble's the size of a school bus. James Webb is the size of a tennis court, just to give you scale. It's a 6.5 meter deployable multi-mirror telescope. It works in the infrared. It overlaps in wavelength with Spitzer, but essentially JWST is giving you Hubble resolution at mid-infrared wavelengths, and it's going to be highly complementary to ALMA in terms of the kind of science that it will do. It's going to be located at L2, so 1.5 million kilometers out in a sort of Lissajous orbit round about L2. It won't be serviceable like Hubble, which means we have to get it right first time. It's basically one of the main reasons why it's out there is that you can then use the shield to block off the moon and the Earth as well as the sun. So you need to get down to 50 Kelvin, so you really need to have this shielded against all kinds of scattered light. The advantage of being out there is that you can do a lot longer integrations, although there are complications in terms of observing with Webb, and that you have to maintain, because you've got this giant sunshade, you actually get light pressure from the sun that gives angular momentum. There are small rockets for propellant, with propellant on there that are used to adjust that. You have to lose angular momentum every so often. So how you observe has to take that balance into account, because you can gain angular momentum. If you do a bad observing program, you can end up expelling a lot of propellant. So observing with Webb is going to be good because you can do long integrations, but complicated for us to actually schedule. Why do we have Webb? Well, this is the sky brightness as a function of wavelength, 10 microns. This is what it looks like from the Earth. This is what it looks like from space. So essentially, you're up to almost 10 orders of magnitude advantage working from space in the mid-infrared wavelengths. That's why you go there. You don't have the atmosphere in the way. And when it comes to doing imaging, this is a comparison. This is the efficiency of JWST against a hypothetical 30-meter ground-based telescope. And Webb actually wins for imaging. Even though it's 6.5 meters, longward of about 2 microns, it beats the ground because of the background. It should also be much more stable, although stability is going to be an issue there. And controlling Webb is going to be a really big issue. So this is what we'd expect to see. So this is the Hubble the ultra deep field. This is what Hubble sees at optical wavelengths. This is what JWST, actually no, this is the infrared image. This is from the WIF-C3 infrared camera. So JWST will give you a substantial gain in resolution in the near infrared. Essentially, you're going to get the resolution will be comparable to optical resolution with Hubble at near infrared and mid-infrared wavelengths. The instruments, there's the NIRCam, the near infrared imaging camera, 0.6 to 5 microns, 2.4 by 4.4 arc-minute field of view. It's diffraction limited, and it has some coronagraphs in there to do high contrast imaging. NIRSPEC is a multi-object spectrograph. We'll come back to that in a minute. The way that the multi-object works is there's multi-shutter arrays, so you can actually observe targets, lots of targets across the field by opening and shutting these tiny mirrors here. 3.4 by 3.4 field of view, 0.1 arcsecond pixels, relatively low resolution, 1,000 to 3,000, and then there's a very low resolution prism. There's also an integral field unit. So that's basically imaging spectrophotometry. So you're taking, within a 3 by 3 arc second unit, you're basically imaging the sky at diffraction resolution. Or actually, you should be imaging an object at diffraction resolution. Miri, the mid-infrared instrument. I guess I should say NIRSPEC. The team building NIRSPEC was led from STEC, and the team building Miri is also a strong European component. ROE, Julian Wright at ROE was the project scientist for that. So Miri, surprisingly, from its name, works at mid-infrared wavelengths. It's about 1.9 by 1.4 arc minutes imaging. Low resolution spectrograph. It also has an integral field unit, and then it also has coronagraphs. So again, you can do high contrast imaging with Miri. And then finally, NIRS, which is essentially, this is the fine guidance unit can also be used to take some essentially grating spectrometry. It's a relatively small field of view. Its main purpose is to lock onto guide stars and guide the telescope. This is the Canadian instrument. So it's the most polite instrument on the system. Launched by Ariane from Kourou. Launch date, October 2018 is what we're fixed to. And we can talk offline about the interesting budget and Congress and so on for the last few years. But we're locked in now. We have the right funding profile to build the instrument and get it launched at this date. And we also have a requirement that if we go over the budget limit, they're going to shoot us. So this date is pretty firm, and we actually have the resources to make it. I'll show them a little video about this later, perhaps. But there's lots of hardware there. We have the mirrors. They're all built and coated now. This is a real person. It's a big instrument. The four main science themes of JWST, well, birthplaces of stars and planets and life are two things that are obviously directly relevant to what we've been talking about here. It's going to do first galaxies. Everybody knows that. Moving on. It's going to look at resolved stellar populations in the field. This is the field of streams again. Basically, within all these clusters there, JWST will be able to get really deep, going down to 30th magnitude, color magnitude distributions. But what might be most interesting here is what NIRSPEC can do. So this is actually an image of omega Sen with the NIRSPEC microshutter arrays superimposed on top of it. And the interesting thing is that even in omega Sen, there is sky there. What you can do is, the microshutter arrays are controlled, each one controlled independently. You can open shutters to pick out stars. This is something that's obviously going to be used for looking at crowded star-forming regions. You can select a very, you want to make sure that the spectra don't overlap on the detector. There's software that will allow you to do that. But essentially, you can do multi-object imaging, long exposures of star-forming regions at near-infrared wavelengths with this device. I think it's going to be a very powerful way of probing much deeper into star-forming regions than anything that we've done in the past. I think this, yes. So yes, it's NIRS as well can provide imaging, field imaging, but it's essentially a grating, so it's not going to give you the separation. It doesn't have slits in it in NIRS. Okay, so the discovery potential. This is an interesting diagram that Jason Callery put together. So this is when Hubble was launched. This is what it was supposed to do. The extragalactic distance scale, origin evolution of the solar system, intensities of supernovae, gas and galaxies. There's a whole bunch of other things that came up after Hubble's launch. Areas that it has had a profound effect, supermassive black holes, lensing and dark matter, looking at stellar populations beyond the Milky Way. Dark energy, obviously, dark energy is something that was not even there as a concept when Hubble was launched. So I think the main impact of James Webb is going to be what we haven't thought of what it's going to do before we launch it. And one couple of things, the star formation rate and the star formation efficiency and the initial mass function may well be things where it has a big impact that's not foreseen. So just looking forward, 10 years from now, ALMA is going to be operating, Gaia is going to be complete, I think. And they'll probably still be working on the data reduction, but that's fine. JWST should have been running for 3 years, and all 3 of those. The other thing I should say in there, I guess I meant to put it down, is there'll probably be there'll be a vestigial EELT probably built in Chile. I think that's going to be the first very large telescope that's up and running. All of those are going to be great for star formation and star cluster investigations. So I think we're going to have some really powerful tools available to us over the next 10 years. So I think it's encouraging. So, and you're the guys that are going to have to do this, because we're all going to be far too old and tired. Thank you.